pretty much everyone who has done something very, very important in C++ is here at least every other year or so. Directly interfacing with those people is just an incredible boon to your career, especially early in your career. Getting to pick people's brains on things, just hanging out, talking with people, you can't put a price on that. And you don't get those online.
All right, good morning, everyone. Hope you guys are all enjoying the conference so far. I'm Ben Sachs. My company, Sachs & Associates, offers training in C++. And let's go ahead and get started because there's a lot to cover. So there are multiple features in the language that allow us to have multiple functions with the same name, which means that when the compiler encounters a function call expression, like the one we see on screen here, it's got to consider all of those features. It needs some way of working out which function you actually intended to call. And so that's what we're going to be talking about today. Because if you have a good understanding of how those features fit together and interact, I think you can use that knowledge to craft interfaces that are really nice, that are flexible and easy to use correctly. But if you don't have a solid grasp of that, you can wind up creating interfaces that are much more challenging for the typical user. So we're going to talk about several features. We'll start off with overloading, then name lookup, default function arguments, and function templates. And we'll talk about each feature individually, and then I'll add on how they interact with the other features at the end of each section. And then we'll close with an example that ties several of these features together. So let's go ahead and talk about function overloading. So the question with these back to basics talks is always how basic to go. So I suspect that a lot of you guys are familiar with some of the basic terms, but I want to make sure that people are on the same page. So functions are overloaded if they are declared with the same name in the same scope. So here on the screen, we see a set of 4 overloaded put functions that take different argument lists. And so when the compiler encounters a call to one of these put functions, if all of those declarations for put are available, the compiler needs to go through a process called overload resolution to figure out which of those put functions I was trying to call at any time. Excuse me. So it looks at the number of arguments in the call, and it looks at the types of those arguments, and it attempts to match those up against the function parameters as they appear in each of the function declarations. Now, it's possible that the compiler won't find any matches at all. For example, none of the put functions that I showed took 3 parameters. So if I tried to call put and pass in 3 arguments, the compiler would simply reject that, would say, there's no function called put that satisfies that criteria. That said, the types of the parameters need not exactly match the types of the arguments that I've given in the call. The compiler is willing to perform some conversions in order to try to find an appropriate match for the call that I'm making. So, for example, I based those put functions on parts of the standard C library. And if you look at the standard C library, you'll find some functions called getChar and putChar that are intended for reading and writing a single character. But they actually operate in terms of a parameter of type int, because in C we use the integer value EOF, which isn't necessarily representable as a character, to indicate things like the end of input. And so put char also works with an int for compatibility with get char. And so these overloaded functions here, these two put functions that I've written, are essentially C++ equivalents of different versions of the put char function. And they both take int as their first parameter type, or at least that's what they're declared to take. But I can go ahead and pass a char to either of those functions. And the compiler will happily convert that char into an int as part of making the call, assuming that that is indeed the best match. Depending on exactly what I wrote, where the argument is coming from, things like that, that transformation from char into int might involve some runtime code, or it might be a transformation that happens entirely at compile time. Which means that among a group of functions, it's possible that there could be more than one function in the group of overloaded functions that can actually satisfy one particular call. So here we see a set of functions all called f, and the first three of these four functions could all potentially be the function called when I pass in 0 as the sole argument. The fourth one expects 2 arguments. That one's clearly out if I just pass in a single argument. But the other 3, these are all possibilities, because 0 could be interpreted as an int, or it could be interpreted as a long int, or it could represent a pointer value that is the null pointer value. So how does the compiler choose between these different functions? The compiler has a ranking system by which it tries to judge which conversions are conceptually easiest, cheapest, you can think of it, in order to decide which of these functions is the best match for the argument types that are provided. And so the function that gets chosen depends on the exact argument type as well as the exact way that the function parameter is declared in the declaration. So when I call f of 0, that's going to depend on what exactly is the type of 0. And, okay, obviously 0 is an int, right? Well, is it signed or unsigned? In this case, it's actually signed, but there are ways you can attach little suffixes to the literal to make it unsigned or to give it a different type if you need to. But in this case, with just the literal 0 with no modifiers, let's look at the 3 options that we have here. So the f that takes an int, well, 0 is an int, that's an exact match. So that's pretty good. There's also the f that takes a long int. That would involve converting int into long int, which would be what we call an integral conversion. And I'll show all of the different conversions that are possible in just a moment. And then there is the idea of converting the 0 into a pointer value. That would be a pointer conversion. So the exact match is, I think, pretty clearly the best choice in this situation. That's essentially that's always going to be the cheapest option in a conceptual sense, because there's no work at all to do there in converting int into int. It already is the thing that we want. So exact matches are going to be the obvious winner when we have that option. So now let's get rid of the f that takes an integer, and let's ask what happens now. Well, in this case, actually the compiler gives me an error. It actually doesn't choose between the other two f functions as options. And the reason being that, as I said, the compiler has this ranking of the conversion type, of the different conversions. And the conversions are ranked in a table that looks sort of like this. And all of the ones that are, so up here at the top, we see exact match. Everything that's off to the left here, that's all at effectively the same rank. So there are things that are lumped under exact match that aren't necessarily an exact match, like adding a const qualifier is considered to fall under the heading of exact match. But then, and then below that, we have the integral promotions, well, numeric promotions, and then conversions. And of the built-in conversions that the compiler will consider, that last category, conversions, is the most expensive. And in this case, converting a 0 into a long int, that's an integral conversion. Converting a 0 into a pointer, the null pointer, that is a pointer conversion. Those are considered to have the same rank. So they look equally good to the compiler. So at that point, we have a tie. The compiler doesn't know, looking at the call, it can't infer from the information that I've given it which of those two functions I actually intended to call, so it will throw the question back to me in the form of a compile error and effectively tell me as the programmer, I need a new hint. Give me some more information to go on, do something to steer this function call in one direction or the other based on what it was that you meant it to have happen here. Now I'll get a slightly different error message here from what I would have gotten in the earlier case where I passed in 3 arguments to the function and there were no functions that took 3 arguments. There, the compiler probably would have said something about there being no matching function among the f's. That is, once it weeded out all of the impossibilities, there was nothing left. All of the f's were gone. Whereas in this case, once it had weeded out the impossibilities and then looked at how the remaining candidates in that, among that overload set, as we call it, looked at how they compare, at least 2 of them were equally good in this case. In this case, there were only 2 of them to consider, but it could be more. In which case, the compiler will complain that the call is ambiguous. It's not clear which of the multiple candidates that are remaining was the one that I had in mind for the call. Now, by the way, that only happens because I chose the literal 0 in this situation. Because 0 is the only integer that will automatically convert into a pointer type. If I had passed in an object of type int or any other numeric literal, then the pointer conversion would have been out and the compiler would have realized that I was trying to call the f that takes a long int in those situations. So that deals with the question of how the compiler handles overload resolution if there are functions that take a single argument. But how does the compiler perform overload resolution when there are actually multiple arguments involved in the call? So here we see a couple of f functions. The first one takes 3 doubles, the second one takes a double, an int, and another double. And then we're going to attempt to call the function f, passing in a double, 1.1, and then 2 ints, 2 and 3. Now, if either one of those functions existed by itself, if I got rid of the other one, they're both valid calls because there are conversions that let me turn an int into a double. And so, but if they are overloaded, which one is the best match. And the rule is that if we have a set of overloaded functions, and here I'm going to say those functions are numbered f1 through fn, where n is however many overloaded functions there are in the set. One function is better than another function if, for every argument, function 1 is better than function 2 if, for every argument in the call, function 1 is at least as good a match for that argument as function 2 would have been. And function 1 is a better match for at least one argument than function 2 would have been. So in order to have a unique best match, there's got to be one function that looks at least as good as all of the other options in every category, for every argument being given, and that clearly wins over any of the other options in at least one category. It can be a different distinguishing parameter for each call, but in this case, we have a function that, again, a function that takes 3 doubles and a function that takes a double, an int, and another double. And in this case, the call with double int int, that winds up being a call to the second option because, well, the first and third parameters are both double in each case. So there, it's a tie on those two parameters in both function calls. For the second parameter, int is an exact match for the 2, whereas converting the 2 into a double, that's a floating point conversion. So the compiler chooses the second option in this case. Okay, so overloaded functions, I mentioned that they share the same name, which means that the name by itself isn't enough to identify a function. There are other properties associated with each of the overloaded functions that set it apart from the other functions in that overload set. And we refer to those properties as the function's signature. So usually we think of that as being the function's name and its parameter type list. So the list of types that the function expects to receive from its caller. So here, for example, we have one of the standard operator new functions, one of the things that is on the back end of the keyword new when you use it. The parameter list here is std : size t and std : aligned val t. Here, the names of the parameters as declared there don't matter. It's just the function name, which in this case is operator new, and the parameter types. Now, interestingly enough, exactly what makes up the signature of a function sort of depends on what kind of function it is. So a non-member function, the signature includes the enclosing namespace, if any. Whereas a class member function, the signature includes the class of which that function is a part, and it also includes things like whether the function is a const member function or whether the function is a volatile member function, that's the CV qualifiers, and reference qualifiers, so whether the function is specifically intended to operate on L values of the class type or R values of the class type. That's a less commonly used feature, but that just gives you some idea of the different things that go into the function signature. Again, it depends on, there are other possibilities that I'm not covering here in the full set, but that gives you some idea of what contributes to the signature there. Okay, so moving on to name lookup. So as the compiler reads through your code, some of the things that we'll see in the code are declarations for things, functions, objects, class types, etc., that are going to be part of your program, names you're going to use later on. And so as it encounters those declarations, it stores that information in something called a symbol table. And then later on, when the compiler encounters a name being used somewhere in your program, it goes ahead and it looks up that name in the symbol table and uses that information to figure out if your code makes sense, for one thing, and then figure out what exactly it's trying to do. So in this case here, the first line is declaring the class widget. So it's introducing the word widget into the program. The compiler sees that, it stores that information in the symbol table. The first member function declaration for the function name, the name string, the user-defined type, that must already be in the symbol table. I should be including the string header before this. And I'm imagining that it is here, it's just not visible on the slide. So string is being looked up in that situation. Name, that's the name of the function being introduced. So that gets recorded in the symbol table as one more thing that the compiler might need to look up as it goes forward. And then as I make use of strings and widgets inside my program, it'll go ahead and recognize when I'm declaring an object S of type string down here, when I'm declaring an object W of type widget. So these are looking up the names string and widget and storing the names S and W in that case. And then the last line down there is all lookup. It's not introducing any names, but it is looking up the names S, W, and name, all to figure out what is that line actually doing. So I think spelling it out this way makes you realize just how much the compiler is actually doing to some regard. And yeah, it really does have to do all of this. So those declarations, part of the information that the compiler records in the symbol table is what's called the scope of each declaration. So declarations can appear at local scope inside a function declaration, which includes the function's parameter list, or also blocks like inside the body of an if statement inside the function. And those names last until the end of the function or the block in which they are declared. They're in scope until that point. Names declared at class scope, these are things like members of a class, either functions or data members. And these names are in scope inside the class body, inside the class definition down to the closing curly brace semicolon, and then they come back into scope in each of the member function definitions of the class type. So the scope doesn't have to be contiguous. The scope is the region of the program where that name is valid and refers to a particular object, and that can be different sections throughout the executable code. And then we also have namespace scope, where this is names declared outside of functions or classes or other class-like things like structures and unions. And names declared at global scope, the global scope is considered to be effectively just another namespace in C++. It's actually referred to as global namespace scope inside the standard. And those names last until the end of the namespace definition, or in the case of the global namespace, until the end of what we call the translation unit. effectively the CPP file in which the name appears. Now, names appear in two different ways. There are what we call qualified names, which are names that appear in the context of another name, to the right of a colon, a dot, or an arrow, something that selects a member from some other category. And then there are unqualified names, which, well, don't appear to the right of one of those symbols. And so here, for example, string is a name is an unqualified name here. A sign, since it's to the right of a colon, that is a name being looked up. That is a qualified name. And the same thing is true in the case of other. Other is an unqualified name. Length is a qualified name. And notice in the final example, the array index I, that's also an unqualified name. It's not to the right of a colon, a dot, or an arrow. So it's looked up using a process called unqualified name lookup. And the lookup processes are different. Qualified name lookup, pretty simple, actually. If the name, it depends on whether the qualified name is appearing to the right of a colon, or a dot, or an arrow. But in any case, the name n here, the thing that appears to the right, that is looked up in the scope of whatever it is appearing to the right of. So in the case of a namespace, it's looked up inside that namespace. In the case of a class object or a pointer to a class object, it's looked up in the scope of the class. And if the name n isn't found in that class scope directly, if there are base class scopes to consider as well, then the compiler will go back and will fall back to using the base class scopes starting from the most direct base class. And if it doesn't find the name being declared, that's an error. Name lookup for unqualified names is built on the back of name lookup as it exists in C. So here we have a function f at namespace scope. We have other variables m and n at namespace scope. Inside the function f, when I use m, since I haven't introduced a declaration for m inside f, m refers to the namespace scope value, whereas n, since there is a function parameter called n, that it's the local parameter that takes precedence in this situation. So the rule for unqualified name lookup when you're talking about non-member functions is first look in the local scopes, starting from the block in which the name appears, in which it's being used, and working outward to the global scope. And then if we don't find a declaration for n anywhere in there, go on and look at the namespace scopes that enclose the function in which this line is appearing, and work our way out to the global scope, stopping as soon as we find at least one declaration for n. And if the name isn't found, the compiler declares that an error. When we're talking about names that appear at class scope, so inside a class definition or a member function, classes add one more place to look. So after looking at the local scopes, again, starting from where the name is being used and working out to the function as a whole, it then looks at the class scope, starting from the class itself of which this is a member, and then going and looking at the base classes starting from the most direct base class, if there are base classes there. And if it finds the name in any of those places, it interprets that name as being a member of that class. And if it doesn't find the name at class scope, then it will move on to namespace scope and search for the name there. stopping, again, as soon as it finds a declaration for the name. So that covers name lookup by itself. Now, name lookup and overload resolution are different steps in the compilation process. So when the compiler sees a function name like f being used, the first thing that happens is name lookup takes place to go and find functions by the name of f. And then if the name lookup succeeds, it might find one f, or it might find several f's that are declared in the same scope, meaning they're overloaded, in which case all of those different f's at the same scope, those become the candidates for the function call. And then overload resolution is used to choose between those different candidates. And as before, overload resolution has to find a unique best match, or else it's considered a compile error. And it doesn't matter if there would actually be a better match in an outer scope. Once the compiler has found a name, has found a set of names, those are the only names it will consider. If none of those are a valid match, name lookup doesn't restart looking for a better match. So in this case, for example, I have 4 functions called put declared on this slide, but they're at 2 different levels. 1 and 2 are at global namespace scope, whereas 3 and 4 are members of namespace n. And then the function f, which is also a member of namespace n, calls the put function. Name lookup will find the put functions at 3 and 4 first, and it will stop there. It won't consider the functions on lines 1 and 2. And in this case, since C is an int, neither one of those functions that takes a pointer to constant character is a valid match. So the compiler will give me an error message that says no matching function. And similarly, when I have a function in a derived class with the same name as a function in the base class, the function in the derived class hides the name from the base class. So here, if I have a base class that has a function f that takes an int, and then the derived class introduces another function f that takes a double, then when I go to call the function f on a derived class object, even though the f that takes an int would seem to be the better match, because the compiler looks in the derived class first, it chooses the function from the derived class, and it never actually sees the function from the base class. Now, I said the names have to be in the same scope. That was a little bit of an oversimplification, because there's one other facet to consider here about name lookup, what's called argument-dependent lookup. And this specifically applies to unqualified function names in function calls. And the argument-dependent lookup rule is when there are arguments in the function call of user-declared types, where those types come from a namespace, include that namespace from which that type comes in the list of places to search for the name of the function. So here, if we did not have argument-dependent lookup, here I have a namespace n that contains a class t and a function f that takes a t by reference. If I tried to call just f of x without specifying that f is a member of n, again, this is if we didn't have ADL, we do. As it happens, in real life, this line would compile, but in this imaginary world without ADL, it doesn't. We would need to manually call the function as n::f of x. And you might look at that and say, okay, big screaming deal. I mean, so I I need to qualify the call. What's the big problem? It really has to do with overloaded operators. It has uses outside of overloaded operators, but the main motivating case is, suppose that that namespace n was actually the std namespace, and that the class t was string and the function was actually an overloaded operator like the output operator. Then that would yield this sort of simplified version of the string header. Greatly simplified. The real string header doesn't look very much like this. You would see it as something much more complicated. But if we go ahead and use this simplified version of the header, then when I created an object of type std : string, if I tried to write that to cout, the compiler wouldn't find the operator arrow function. And in fact, it wouldn't find it even if I deliberately called it as operator arrow, like it was a traditional function. Neither of those lines there would work. I would have to explicitly say that I was calling the operator arrow function from the std namespace. Fortunately, I don't have to do that. So the previous calls would work in real C++, but that gives you an idea of what would happen if we did not have argument-dependent lookup in the language. Excuse me. So this led to Herb Sutter declaring what he called his interface principle. I have to admit, I'm always a little bit weirded out quoting someone who I know is at the conference, but you know, it's not like it's a new book. It's just he keeps coming to these things. So the interface principle is when you have a class X, functions that are part of the interface of X, which includes not just member functions, but free functions that use objects of type X and that are packaged along with X in terms of being a header file, part of a header file, those should be in the same namespace as X itself, because then argument-dependent lookup will be effectively enabled for those free functions that are meant to be associated with X. So this operator, this overloaded operator, should be in the same namespace as the type string there. So the advice is if you put a class into a namespace, put all of its interface functions into the same namespace. Otherwise, you might be in for a surprise. So overload resolution also considers names found by argument-dependent lookup. And those names are not given any special treatment. They're added to the candidate set of possible functions just as if they were found through ordinary unqualified name lookup. Okay, default function arguments. So in the standard C library, there are a number of functions that take parameters of type pointer to file in all caps, which can be a file or it can be an output stream. So earlier I showed you these two put functions, and the top one always writes to standard output, whereas the second one writes to a file or to a stream. I could actually write these two functions in C++ as a single function with a default argument of stood out for the second parameter. If I did this, I would get slightly different code as a result. When I write the put as a pair of overloaded functions, then there really are two different put functions, each with its own signature, int or int and pointer to file. Whereas if it's a single function with a default argument, then there really is one function on the back end that takes an int and a pointer to file. It has the same signature as the second function in the previous example, in the overload case, would have been. And the default argument value, that's not part of the signature here. So this really would result in you would not see multiple functions in your generated code. Now, how expensive in an overload resolution sense is it to fill in a default argument? Turns out it's considered free. So if we have two overloaded functions here, g, one that takes a double, one that takes one or two integers. If I call g on the literal 0, well, turning the 0 from an int into a double would be a floating point conversion in the first case. In the second case, we have an exact match because 0 is already an int. That's an exact match for the first parameter. And filling in the default argument for the second parameter, that's not really considered a conversion of any kind. That we get that for free. So it's the second g function here that takes two ints that gets chosen as the winner. Okay, onto function templates. So function templates are not really functions by themselves. They're generalized recipes for functions that can be used to generate several functions with the same name. So for example, if you were to look at the standard header algorithm, you would see this function max or something like this, which just finds the larger of two values. And when we go to call a function like this, we can supply the argument, the template argument manually, or we can let the compiler deduce it here. So I can just call the function as max and let the compiler figure out that I mean max of int using what's called template argument deduction, just by looking at the types of x and y in that call, which makes the max function template look more or less like an unbounded set of overloaded functions. Just every time I call max, passing in some new set of argument types, as long as the compiler can make sense out of them, it will generate a new function using the max template that takes arguments of that type. Now, I can manually specify the type argument if I want to. And there are occasionally reasons to do this, because these two calls here actually produce slightly different behavior. When the compiler is performing template argument deduction, it doesn't consider most conversion sequences. So, although normally, in a typical function call, the compiler would be willing to convert an int into a double, as one of those floating point conversions that I mentioned before, if I were to call the max function template, passing in an int and a double here, the compiler wouldn't be able to make sense out of that because it's expecting both arguments to have the same type for whatever type it's going to fill in, and it would reject this call as saying, it's not clear whether you mean to be calling max on two ints or two floats, or sorry, two doubles in this situation. On the other hand, if I explicitly specify the type argument, then it's clear I've taken the options away from the compiler. It treats it essentially as an ordinary function call where the types of the parameters are known. And now it will consider all of the usual conversions. So if I called max of double specifically, then the compiler would happily convert x into a double for the purposes of making this call. And similarly, I could instead call max of int, and then it would convert y into an int to make the call to max. So sometimes I use this approach of specifying the template argument manually as a way of resolving that kind of conflict for the compiler. Now you can also overload functions and function templates. So you can have non-template functions overloaded with the same name as a function template. And the rule in that situation is that if a function and a function template look like they are equally good matches for a function call, then the compiler will choose the non-template function as the better match. The assumption being that if I went out of my way to write a non-template function in addition to the function template, I must have had a reason to do that. And this lets me do things like I could write a customized max function that takes in pointers to constant characters, so C-style strings, and uses strcomp to differentiate between them, to choose whichever string would come later in the dictionary. I don't think this is necessarily a good interface design. I wouldn't recommend that you do something like this. This is just a simple example to show the kind of thing that you could do here. We'll see something else that I think is a little bit more realistic, better advised a little later on. So in this situation, if both the max function template and then that non-template function, max, that takes pointers to characters, were both overloaded with each other, then if I went ahead and I tried to call max passing in arrays of characters here, that would call the non-template max function, because they look like equally good matches, and so the non-template wins out. I could, if I wanted, call the max manually, specifying the template argument, and then it would call the template version if I really wanted to. I can't say that I've ever in practice found a reason that I wanted to do that, but it is a possibility. All right, so those are the individual pieces. Let's talk about how they work together. So I think the most common example in which these features combine is what Eric Nabler called the std swap two-step, which is essentially a programming technique that allows for what we call customization points. Now, customization points are a big deal for people writing libraries, particularly libraries composed of function templates, because they allow you, the user, to customize the behavior, to provide an improved version of some algorithm or some function, if they choose to do so. But they're usually designed in such a way that it will fall back to something more standard. So in this case, in the typical example, the customization point is a swap function. So the algorithm header also contains the std swap function, which might look something like this. And it works for a lot of different types because it operates in terms of basic move semantics. That said, it's still not necessarily the most efficient way to swap two things, even if a type supports move semantics. So earlier I had a sax : string type that I presented. If I were to write a custom swap function for that string type, I could probably make it more efficient than the swap behavior that I would get from the standard swap template. And here I've written it as a non-member friend function. You'll see why I've done that as this example goes on. But here is a function, a version of the swap function for those sax strings that I think would probably beat the performance of the standard swap. It just simply swaps the individual data members, and so it's copying the pointers around rather than having to do things like empty out the array in the object that's being moved from. So that's nice. It's nice that I can improve the behavior of swapping for my Sachs string type, except that depending on how someone uses this, they might still get the standard swap function by accident if they're not careful. So here, let's suppose that someone else comes along and they write a type person that includes a Sachs string object as one of its data members. And then it has a swap function, which in this case I've made a member function. Probably that should be a non-member friend function as well, as we'll see. But I wanted to keep to minimize the potential for confusion there. So if I didn't know, as the author of person, that the Sachs string type has a custom swap function, I might go ahead and write the code for person's swap function, something like this, in which case I deliberately call std : swap on Sachs strings, and then I get that standard version of the swap function rather than the customized version. So fortunately, there's a technique that we can often use to make sure that we can avoid that mistake, and it looks like this. I add a using declaration for std swap to this function block, and then I call the swap function without the std : qualifier. So then, in this case, the compiler actually will figure out that what I mean is for the first swap to use the Sachs : swap function, and for the second one to use the std : swap function. And what it's doing, the technique is not that difficult to apply, but what's actually happening here is when I was calling std : swap directly, there the compiler is using the qualified name lookup process because swap appears to the right of a : . So it goes directly to the namespace std and it just searches for swap there. And that's where it finds the swap that it would then go ahead and use. But when I call swap as just swap as an unqualified name, then this code uses unqualified lookup instead, which means that the compiler will follow the unqualified name lookup process and it will search outward from the point of the call, looking for declarations of swap, and it will also consider argument-dependent lookup in this situation. Again, argument-dependent lookup occurs only in unqualified name lookup. So that local using declaration, using std : swap, that pretty much immediately stops the normal unqualified name lookup process, because as soon as the compiler searches for the name, it immediately finds it in the very block that we're looking at. This acts like a local declaration for the std swap function, puts it at the very front of the list of places to search. So the std : swap function template, that gets considered to be one of the candidates for the calls to swap. And then the compiler performs argument-dependent lookup, and it finds the swap function that's in the Sachs namespace here. And so it adds that function to the overload set that it's now got to consider. Both of those are now candidates, and the compiler needs to use overload resolution to choose between them. So both of them take two arguments of type string. That is, if you specialize the standard swap template for Sachs strings, they both look like they take the same arguments. So they would both be considered exact matches in that situation. But std swap is a function template, whereas the Sachs : swap function that I wrote by hand, that's not a function template, it's an ordinary function. So that wins as the best match in this situation. and the compiler chooses to call that function for sax strings. Now, if there hadn't been a sax : swap function, then std : swap, that would have been the only option. So the compiler would have fallen back to that. And so that using std : swap there gives me the ability to write my own swap for the types that I'm interested in and have the function automatically use that instead. But if I choose not to write that, then the compiler will find the std swap function using the ordinary process. It'll fall back to that, which is very nice. I think it's a very helpful technique that library authors often use and that we can apply as well, because we don't want to have to, if we go look at this, we don't want to have to remember in general whether the swap function is a custom function or not. Ideally, we don't have to think about that because especially maybe the function doesn't exist yet, but I choose to write that function at some point in the future when I recognize that swapping sax strings is a little more expensive than I thought it would be using the standard swap function. If I follow this kind of approach, I can do that, and this just automatically updates to use the custom version on the next time it's compiled. Now, important notes, this works specifically because they're both non-member functions. Both standard swap and sax swap are both non-member functions that take two arguments, so they're called in the same way. If the swap function had been a member function for sax strings, then the call would look different. And then there's no question about which version of which swap function the compiler would need to use in these situations. It wouldn't have the freedom to consider both options. So that being the case, I should probably be writing this person : swap function as a non-member friend function as well, to allow for this to be a custom swap in the future as well. And it's also important that the sax : strings swap function was in the sax namespace so that it was found by argument-dependent lookup, because the ordinary name lookup process stopped almost immediately when it found std : swap, a declaration for that, local to the function. So there really isn't anywhere else that the custom swap could be where it would wind up being selected as a candidate. So I think the big takeaways here, name lookup and overload resolution are separate processes, and name lookup happens first. In general, when you have a class in a namespace, you should follow Herb Sutter's advice and put helper functions, other related operators in the same namespace so that ADL will take effect. If a function and a function template are equally good matches for a call, then overload resolution will favor the non-template. And try to be aware of customization points. And when you can, make use of things like the two-step technique to make sure that you're calling the customized versions of functions when possible. It's not the end of the world if you don't call a customized version, but might make your code that much more efficient. All right, that brings me to the end of the talk. So yeah, I think we've got a couple of minutes for maybe one question. Yeah. And if you would come up to the mic to use that.
So is having a function declared as static in the class the equivalent of having it in the same namespace?
A static class member function,
Yeah.
and that's still in the scope of the class. And so it would, the name lookup process, unqualified name lookup, would find it when it looked at the class scope, the same way that it would find a non-static member function.
So
Yes.
it could be used for the two-step swap technique to put it static inside the class instead of in the same namespace.
I'm thinking about that. If you wanted to, I'm not sure off the top of my head. I would need to try it. Yeah, if you stick around afterwards, I'll try and get on Godbolt and we can actually try it out. Yeah, off the top of my head, I'm not actually sure whether that would work or not, because it's not a namespace, and I think that the argument-dependent lookup rules really are specific to namespaces. So I feel like it wouldn't work, but I'd have to check it to make sure.
All right, thank you.
All right, thank you all for coming. I hope that you enjoy the rest of the conference.